Hello, everybody. My name is Petr Kluson, and I'm Scientific Vice President of the European Federation of Chemical Engineering. And I'm very, very happy that we can be together this afternoon. We have a lovely program ahead. Markus, Busch, and Kristina Zentel were so nice that on behalf of their working party, they decided to organize the webinar within the Spotlight Talks, which are organized this and next week by the European Federation. I'm very glad about this, and I'd like to express my thanks because we see it as an essential activity besides the European Congress of the whole EFCE. And without this work, and without your participation, and without being here, and without the lecturers today, it would not work. So I'm very, very grateful. Martin, who is head of the Secretariat, Scientific Secretariat of EFCE, definitely thinks the same. Martin, I guess that you do. All right. So before going to the webinar, I'd like to warm up the soup of European Federation. Martin, may I ask you for putting the one slide? I'd like to draw your attention to another activity which is coming very soon on 5th of December. So in nearly 2 weeks, we are actually opening a completely new section of the European Federation, which is called a section on chemical engineering as applied to medicine. It's a one-day long seminar with plenty of interesting lectures, and we have still there few empty spaces, places for attendees. So if you are interested in the topic, how chemical engineering is applied to medicine or could be applied to medicine, this very highly interdisciplinary research, don't hesitate and join us in Paris. So we can close it now, this screen, and I will ask Markus or Kristina, either of you telling us something about your working party, and then we may open the stage for the presenters for our today meeting. So thanks a lot.
Yeah, thanks, Peter, for the introduction, and also from my side, welcome. And I'm really happy that you are here. 60 plus participants. This is, I guess, when I look to Kristina, this is more than we expected. We are extremely happy about that and for the interest. Yeah. Who am I? So my name is Markus Busch. I'm working at TU Darmstadt. I'm working in the chemical engineering department that is grouped here in the chemistry faculty. And we, Kristina and we are working in chemical engineering, and they're on polymerization engineering. We are both talking to you from Darmstadt. So my interest is high pressure polymerization technology. Kristina originated from high pressure polymerization technology and is moving over to emulsion polymerization with a little bit of pressure in addition, so that you can see that you can combine things. So what is polymerization engineering for those who are not directly related to the field or to the working party? It is, as there I will pick up the phrase from Peter, it is chemical engineering applied to polymers. And compared to classical engineering, we have to suffer a little bit because our materials that we form and we deal with have properties, and they have distributed properties. That's the bad news, because we have some extra in characterization and some extras in degrees of freedom. However, the good news, and this is the main task of what we do as polymerization engineering, is with process conditions and process types, we can control the application properties. And this is what our work is about in very brief, and the more extended things you will hear from the speakers. We have speakers from 5 countries, 4 from all over Europe, 1 from the US. This is not that we count the US to Europe, so this would be maybe an expansion target, but it is about that our community is originally quite small. It's a family, and part of the family, a significant part of the family, is on the North American continent, and we tend to include them in all our activities. This is what we love, and this is what we would like to do. So we have one participant also from the US. We have 4 working in academia and 1 from industry, so Petr Singstad. And I think that all of them among us have close collaborations. So I think this is what will be the type of introduction from my side. And then I will hand over to Kristina. Kristina is the heart of this. She is the secretary. She is my right hand. She is my brain if I forget things. So she is putting all the activities in. She may introduce a little bit of herself and her working field. She knows all about the topics and talks we collected. And so thank you, Kristina, for doing all this. And now I hand over.
Yeah, thanks a lot, Markus, for the kind introduction. And thanks to the audience, to the speakers for their interest, and especially for the speakers for their willingness to present. So I had a lot of fun also setting up the Spotlight talk, and I'm happy that we could find such a nice mixture of interesting topics. I hope that all of you will enjoy what we set up. So we will start with a presentation about polymeric foams. Then we will move to a rather big part, which is, I think, very important in the field of polymerization engineering, and that is modeling. Modeling is often directly connected to experiments. That's, I think, something that we will hear in quite a few of the presentations that we can look forward to. And then finally, the last 2 presentations that we will have today, they deal with emulsion polymerizations, different aspects. So that will be what we finish off with before we start into a final panel discussion. And for all the attending people out there, please be so kind and put all your questions into the Q&A tab, which you should find somewhere below in the Zoom menu. And then after each presentation, we will have 5 to 10 minutes directly to answer the questions that you can put in there. I will read them out, we will discuss them. And if there are too many, we will keep them for the panel discussion at the end. Please, if in doubt, add to which speaker your question is aimed, so that we don't confuse questions for the different speakers. So I think that was all that I wanted to say. I think, Martin, we can start with the scientific content. So I want to shortly introduce and welcome our first speaker. This is Juraj Kosek from the University of Chemistry and Technology in Prague. I already had the pleasure to visit this wonderful university and also your lab some years ago when we had our EFCE Working Party PhD student workshop there, and we had a great time. So it's we are happy that you are joining for the Spotlight talks now. And Juraj will talk about polymeric foams, how they are produced. And already here we get a nice comparison between experiments and simulations, if I'm not mistaken. And already also idea about thinking sustainable. So with this, the screen is yours. I'm looking forward to the presentation.
Okay, thank you. I will try sharing my screen and I will start my presentation, and please give me feedback if you see my screen and my presentation in the presentation mode.
Yes, everything is working wonderfully.
Yes, so then thank you, and thank you, Kristina and Markus, for putting this together. I guess that it's a great activity, this Spotlight talk, to enter EFCE community. And I believe that these talks shall not just show like top-line research, but also be kind of educational and show whatever is possible today with, let's say, experiments modeling. And my talk is about polymeric foams, but today we are facing many issues in polymer recycling and many like phase separation problems in polymer recycling are also can be addressed by a similar methodology like development of polymeric forms by phase-induced phase separation. So there is also some common denominator to current challenges. So again, thank you once more for organizing all this activity. I am going to start now with the presentation. So the presentation is of course motivated or originally was motivated by polymeric foams, where current polymeric foams are typically made from commercial commodity plastics like polystyrene, polyurethane, and there are many techniques how to make them, either by blowing agents like physical made foams like polystyrene or polyurethane, or some of them are made by reactive foaming. And of course, we are aiming at improving physical properties of these foams. That means better mechanical properties or better heat insulation properties. In case if we want better heat insulation properties or better sound insulation properties, we have to go to small cells at keeping the same porosity. And of course, we are aiming at reducing the solvents used in production of the foams, like volatile organic chemicals. That means trying to use some biosolvents and so on. And at the same time, we are not just aiming at improving the foams, but also trying to understand the mechanism of their formation and to be able, as a part of the understanding, to do the mathematical modeling of their formation. What I said on the previous slide, we have also here on this slide. That means a conventional polystyrene foam looks like the left picture, which is shown here. Typical size of the cells is above 100 micrometers, and the cells are closed. That means we have walls on all sides of the individual cells. However, when making macrocell foams, we may aim at either closed cell forms that we see in the middle picture. I will try also to improve my pointer if it is possible. Yes, now it's showing better. Or we can go also to microcell forms with open cells, which can have some advantages. For example, in the sound insulation, the open cell forms typically work better, and the smaller are the cells, the better sound insulation material it is. And of course, the structure on the right side then reminds us also to the scaffolds. So in case if we can manage to make forms from some biodegradable polymer, that could be also great perhaps to applications from bio-based polymers or to applications to pharmaceutical research and so on. So the outline of my talk is over. So I will first introduce briefly the phenomena of temperature-induced phase separation. I will introduce some really extremely simple experiments in this temperature-induced phase separation foaming for polystyrene foams, because it's a nice educational time example. We'll explain how we can model the formation of such a foams, and then we will also cover some results, not again the methodology, because it will be already well known from the first part, how we can make from polylactic acid. So let me start with this temperature-induced phase separation. Generally, it's a phenomena which is very often involved as part of existing foaming technologies, not just the like quart artificial education example that I will talk in a while. Also, when making polyurethane foams, when we typically mix two solutions, one is the isocyanate or diisocyanate solution, one the polyol solution, we mix and wait until the foaming is achieved either by the formation or by the adding of the blowing agent like cyclopentane and so on, or by the production of CO2 by the foaming reaction. And we have similar processes not in the formation of foam but also in phase separation and in formation of the morphology of many important plastics, including, let's say, high impact polystyrene, which is a material from which very often yogurt cups are made. So that what I'm going to talk, it's not something like just for scientific purposes, it's also something very often in used for practical purposes. But let me go to the simplest possible educational example. Very often in a two-component system, polymer plus solvent, we have something what we call upper critical solution temperature behavior. That means phase diagram of temperature against the composition shows us typical shape of a binodal curve with the upper critical solution temperature right here, and inside the domain we have a region of limited miscibility of something what we call polymer rich phase on the right side, and at the same temperature a solvent rich phase on the left side of the same binodal. For example, in the case of polystyrene, we can make some homogeneous solution of polystyrene in cyclohexanol at a temperature which is above this upper critical solution temperature. We don't have to go to really high temperatures, a temperature of 50 degrees of centigrade. We are already in the region of a complete miscibility of a polystyrene and cyclohexanol. Then, from the starting point, we are just trying to quickly cool down entire mixture, and during cooling down we will move to a region of phase separation where polymer rich phase and solvent rich phase will separate, and such a structure can be fixed or frozen by going below the freezing point of entire mixture, and this allows us to freeze the entire porous structure. And then we have to remove solvent either by extraction, freeze drying, or whatever operation we decide to do it. So that's a general plan for the sponge decomposition. So it's really as easy as start from a solution, and only the cooling process will get us to where we want, and you will see in a while what is happening. Of course, to study the process systematically, we have to find out the location of binodal curves, that means the limited miscibility, and the simplest technology of measuring the binodals in the liquid mixing is turbidimetry. That means as long as the mixture is homogeneous, the optical signal is passing through the solution unaltered. Once we get during not just the time but also a slow cooling of the mixture to a demixing, then we have some occlusion of the mixture, and so the light that is passing transmitted through the solution gets scattered, so the intensity of the signal transmitted through the sample gets reduced, and we are able to find out the cloud point. Of course, when continuing the cooling at certain temperature, the cooling rate will suddenly slow down significantly, and that's our position of the freezing point, because at this point further removing of the heat is not reducing temperature, but because of the specific heat of the freezing melting, we are more or less for some time at the same temperature. So that's how the measurement typically works. Such a measurement can, of course, characterize the binodal curves, and these binodal curves, that means a region of limited miscibility, when they are analyzed by this turbidimetry or other techniques very differently. It's not that nice as a nice theory. It of course depends on the molecular weight of the polymer. That means at small molecular weight, the mixing really happens at low temperatures below 20 degrees. At high molecular weights of the polystyrene in the cyclohexanol mixture, we have this upper critical solution temperature close somewhere to less than 30 degrees of centigrade. So we get a some experimental points that characterize the binodal curves and the two-phase region, which is essential for the demixing of the originally homogeneous mixture. Of course, we can describe such a binodal curves not just by the experiments, but also systematically. And for the systematic description, we can use various tools of thermodynamics. In terms of polymer, the simplest thermodynamics that of course has a limitation because we keep a constant volume of the interlattice. It's some theories based on the lattice, and one of them is the well-known Flory-Huggins equation of state based on lattice theory, which says that the Gibbs energy of mixing depends on the entropic term, which are the first two terms on the right-hand side, which the entropic term always contributes to the mixing of the two components, the polymer plus solvent component, plus the enthalpy term, which for non-polar compounds can be described by this model. This rule for the mixing of the two components is quite simple and includes just one parameter he. So it's a really simple theory, and it's also nice that we have just one parameter describing the entire process. Based on the construction of the Gibbs energy, we can identify the binodal points. That means the Gibbs energy curve is this one. The binodal points are the points that are on the common tangent close to the minima on the Gibbs energy curves. And we also have inflection points, which are so-called spinodal points. In between the spinodal points, it's actually the region of the instability, the regions in between binodal and spinodal points, region of the metastability. In the unstable region, it's a region where spontaneously we will immediately observe the phase demixing. In the metastable region, we need a nucleation to start a phase separation, generally as a rule. So when we apply Flory-Huggins theory, combine it with our measurement on the obtained by turbidimetry, we can actually reconstruct the binodal curves, the blue ones for a real mixture, and also we can just by computer construct the so-called spinodal curves. That means the region which is the region of thermodynamic instability inside the region spanned by the red curves. Of course, something similar can be done at the different molecular weights of the polyethylene. That means we can do, in principle, the same process with many solutions. Now, the real experiment is really as simple as this one, the device where we have originally homogeneous mixture of polystyrene cyclohexanol is just some metal cylinder because we have to remove the heat quickly. That means the bottom is made from a copper, and it's put into some pan into which we have a cooling medium. That means, for example, a solid CO2 in ethanol or whatever medium for fast cooling. And we don't really need that much else. So really our entire experimental setup can be as simple as that. When cooling the originally homogeneous mixture of polystyrene in cyclohexanol or different solvents, we can end up with different morphologies. That means the morphology of type A is more or less some aggregate of very or small particles of the size more than 1 micrometer or around 1 micrometer, and it looks like some colloid aggregate more or less. We can also end up with an open pore structure, which is shown in this picture B, or we can end up to the picture D, which are the closed pores, or with some mixture of open and closed pores. The only difference in what we obtained finally in these pictures, it was made from the same mixture of polystyrene cyclohexanol, and the only parameter which was different at the beginning was a concentration of polystyrene in cyclohexanol. That means just by varying the initial concentration, we can get all these morphologies as the only parameter. That means of course, the sum of the parameters is missing is the time scale of the cooling. Depending on the time scale, it also is affecting slightly the details of the morphology, but the principal parameters of the final morphology are affected really by the initial concentration. I will skip a little bit the dynamics of the cooling, which is important to really understand small differences on the morphology at the bottom of our container, which is cooled quickly, and the top layer of the container, which is not cooled that quickly. And we will get more to the mathematical description how to describe this phase separation. This phase separation can be described by, in principle, material balances with some transport fluxes that are not going to be a simple fixed law with flux driven by concentration gradient, but we need a diffusion flux which is driven by the gradient of chemical potential, and we can derive the gradient of chemical potential from the Flory-Huggins equation of state for polymeric system. So that's one trick that we need in order to describe it correctly. And another trick that we need is to add some penalty function for the phase interface, because real systems, they experience some interface tension in between different phases, and they are trying thermodynamically to minimize the phase interface. And for reaching of that, we have to add some penalty function. This penalty function is here the term, the square of the gradient of composition, for example, of the solvent concentration at a given place or polymer concentration given place, and with parameter kappa, which is proportional to the interface tension in between the phases. And otherwise, all of it is applied, of course, on the phase diagram that we already explained. When such a theory is applied, then we will predict the formation of some final structure, and we can compare the structure that is going to be predicted by the model to the origin, to the morphology obtained by the experiments. And we can do this comparison, for example, in the zone of low concentration of polystyrene in cyclohexanol in the beginning of the solution of the process. And by doing that, we can actually set the interface tension parameter, which is a kind of a tuning constant, which is set for experiments of low polystyrene concentration in cyclohexanol. So it tells us some comparison of the experimental and mathematical modeling predicted morphologies that were used to fit one parameter. Then beginning just on the initial concentration of the original mixture at, let's say, 50 degrees centigrade, that we cooled down quickly, we can end up with all morphologies that were displayed on electron microscopy images. That means either particles that we've seen that were not that separated but aggregated, that's what we observed on the electron microscopy images, or we can have the open cells, that means interconnected cells in a three-dimensional structure, or all the way to the closed cell structure where we have closed cells, and the only parameter that is important for obtaining these different morphologies is really the initial concentration of polystyrene in cyclohexanol. Some example of the animation. I will see if it works or not. It was working a while ago in my computer, but now the animation couldn't start in the presentation mode. So I will skip it, and I will show also the structures as they are predicted in 3D dimensions, typical in simulations, the aggregates of the particles, the open cells, and all the way going to the closed cell structures. So that's explanation how we can not just get experiments with various morphologies by this temperature-induced phase separation, but also mathematical modeling, which can be quantitatively compared to the structures. The fitting went only with the original structure with the size of the primary particles. All other structures are purely predictive, predicted by the model and compared to the experiment. That means there is no longer any fitting involved in obtaining other morphologies. The only parameter is a size of the particle in the first structure. Of course, we can apply this process not just as the educational purpose for polystyrene cyclohexanol, but we can try to apply this process for producing foams for different other materials. One of them can be a polylactic acid, and in polylactic acid, it's of course a question which solvent to use and which solvent could possibly work in this temperature-induced phase separation and can help us to, let's say, make foams. In order to do it, we can use so-called Hildebrand or Hansen parameter theory with so-called parameter delta, which is nothing else than the square root of the cohesion energy of the system of the given component square per unit volume or cohesive energy density, and so we can screen different solvent and find out which one possibly can be a suitable one for producing the foam. Of course, many solvents very often are toxic, and we want to avoid the common excellent solvent which are toxic and are looking more for solvent which are like friendly or well known. In this case, for polylactic acid, we found that one of the best solvent that actually works, and later experiments will be shown with it. It's the acetic acid, which is of course even a biosolvent. It works just perfectly. That means it's not that novel, of course, solvent because it's widely available, but which works very well for polylactic acid. Again, we have to find out the binodal curve. That means measure the colloid point curves, find out the phase diagram, and do the same trick in principle as the one that was done with polystyrene foams. And then during the demixing, we can observe these green pictures from experiments and from tomography, where we took a picture of the actual foam structure, and the foam structure now contains not a nice polyhedral type of the cells, but a lamella type of the cells which are typically quite elongated. That's because the interfacial tension between polylactic acid and acetic acid is quite low. So also the Cahn-Hilliard type of the models are producing us the elongated structures and elongated cells. That means that we are actually obtaining the same open cell structure of elongated in principle fashion, both again in experiments and in practical modeling. So it's just the formation. Finally, because I am getting close to my time, because I shall keep the last 5 minutes for the discussion, we can, of course, depending on the original concentration of polylactic acid and acetic acid, get different polylactic foam and try to characterize what's the average pore diameter, which is not ideal quantity, how to characterize morphology of these foams, because the cells are really elongated. So we need at least two morphology descriptors. Better one would be the thickness of the cells and their characteristic length, but nonetheless it's a simple characteristic that we can compare and to see which conditions lead to smaller or larger pores and how we can achieve it. By the way, this polylactic foam is biodegradable, and we can use it for growth of some microorganism or testing of pharmaceuticals and for different applications. So to conclude, in the last slide of my talk, I was trying to explain not just how to make microcellular forms by temperature-induced phase separation, but also what physics is behind, and how can we use a very similar type of the modeling, which is known in the literature as the Cahn-Hilliard modeling, for modeling of the phase separation. Actually, in modern days, we have, due to the recycling, we often face the challenge of demixing of even the same polymers, like polyethylene to polyethylene, low merclovite to high merclovite, are often not compatible. So very often we need to apply these models also for modeling of actual behavior in a mixed polymeric waste, what is actually happening, and which morphologies of the recycled products we will achieve during processing of different plastic waste. So it's also the technology applicable for this purpose. So I thank you for your attention, and in case if there is some question or so, I'll be happy to answer it. So thank you for the attention of everybody.
Thanks a lot. I hope you can hear me again for your presentation. So far, I haven't seen any questions in the Q&A tab. So if some questions come to your mind, feel free to post them in the Q&A tab, and I will read them out. In the meantime, maybe I can start with a short question. Could you go to the slide where you showed us the prediction of the cell size distribution from the modeling?
You mean this one?
Exactly, yes. So I was just curious. So, I mean, the predictions, they are in very different ranges. So apparently some are much smaller, others go up to 10 micrometers and more. But there's still some differences between the experiments and the models. So the order of magnitude is predicted very nicely as far as I understand. Do you have any idea why they differ a little bit with respect to the cell fraction?
Yes. So first of all, again, I will remind that we did just some like fitting from the smallest volume fraction of polystyrene in cyclohexanol. That means it's a morphology resulting in aggregated particles. So here we were just trying to get more or less the same mean value in particle diameter. So this agreement here in the mean value is something which was fitted to interfacial tension. So here we shall get perhaps the best agreement in the mean value. The other two diagrams were completely predictive. That means there was no really fitting of the experimental model. It's just a comparison. What are we obtaining? Part of the reason that we have a, let's say, more broader cell size distribution in the experiment than it is in the model is also the effect that we have a limited domain for mathematical modeling. That means typically it's a dynamic simulation, and the number of voxels we have in three-dimensional model in each direction, it's either 200 by 200 by 200 or sometimes 300 by 300 by 300 voxels, and it's not enough perhaps to really get this broader prediction of the cell size distribution.
Yeah.
Then, moreover, in reality, we will have also phenomena like a coalescence of the bubbles that are close to each other. So, and then also depending on the cooling rate, it means in case if this cooling is not that fast in stillness, but it's a little bit slower, then we are for a longer time in the phase diagram in a zone where the structure is still developing, and this still developing structure, due to the mechanism like Oswald ripening or coalescence of the cells that are close to each other, can really lead to this broadening and to the changes that we are observing. Of course, some of these mechanisms, like the Oswald ripening, is included in the model, but this phenomena of a different rate of the cooling in different part of this of our domain, it's something which is was not captured in this very simple model, which was aimed on demonstration of what is possible.
Okay, yeah, thanks a lot for the explanations, Juraj. So I've had another quick look in the Q&A tab. Nothing popped up there. So also with respect to the time, I think I want to thank Juraj again for the nice presentation. And if questions pop up later, feel free to ask them, and then we can discuss them at the end of our Spotlight Talk session. Perfect. Then we can move on to the next presentation, which will be given by Dagmar de Hooge. He's from Ghent University in Belgium. And we will stay close to the topic of modeling. And he will talk about model-based design and also keep the idea of sustainability and recycling alive in his presentation. So I'm looking forward to it a lot. And you already started sharing your screen, so the screen is yours.
Hello, welcome. You see the full screen because it's not fully working with myself.
Not the presentation mode, so I still see the PowerPoint version.
Yeah. I will retry.
I still see
the testing it worked. But
yeah, too much testing. Maybe you can quickly close PowerPoint.
Yeah, I will close everything. Yes, now it's working. You see the full screen?
Yes, that
Okay.
looks perfect.
But I now need to shift some things with me. Okay, so thank you very much. So my talk will be on model-based design of industrial polymer synthesis and recycling. So as Kristina said, I'm originating from Ghent University, but the work I'm presenting is really in a collaborative context, and two main partners are Stanford University and Karlsruhe Institute for Technology. So first, a bit of a general introduction. My talk is really focused on helping the community to really pinpoint how the molecular scale, and also what Markus said in the introduction, we have distributed properties, how variations chain by chain have an impact on the final properties. If you zoom in here at the top left, we would like to have our polymer chains to be degradable, but sometimes this means that we really need to have, in this case, green units incorporated in the chains and at a good location. And you see here chains that are like almost green and chains that are almost completely blue. But the idea is that with synthesis protocols, we are capable to really put certain monomer units at certain positions. And if you go a bit more to niche applications like here at the right-hand side, we even want to have a specific functionality at one spot and then another functionality at another spot. It's not only about synthesis that we really want to show how molecular variations are occurring, but also when we have a polymeric material. Look here at the solar cell. The solar cell is a multi-layer material and polymer is inside. In this case, we have ethylene vinyl acetate polymer, which is the encapsulant. And if we zoom in, these are cross-linked chains, but during use of the solar cell, UV lights, and high temperature are coming in contact with this material, and degradation reactions start to place. And we need to know which type of degradation reactions are dominant. And we also need to know the location of a certain scission reaction. And also location-wise, is it at the interface or is it really in the bulk of the material? If we then make even a further look where we want to go to desired degradation, like in chemical recycling, when we're doing a synthesis, we have all kinds of molecules interacting with each other. And if we take a radical polymerization process, we have two radicals meeting each other, they recombine, but that red spot here is a weaker point when we would put the temperature up, which we do in a chemical recycling process. And you need to know where the red spots are, simply said, to understand fully the chemical recycling. What I've already shown until now are mainly linear chains. I touched a bit the cross-linked chains here. But in the end, when we look at a material that is, for example, in the pharmaceutical industry, also there we are interested in molecule-to-molecule deviations. And what I would like to convince you about today is that even in very simple chemistries, and simple chemistries is relative, you have the issue that chains are non-identical, and that's why the performance is really dependent on the individual chains. My presentation is divided in two stages, and the first stage is lab scale design. What we mean with that is that the reactor or the flask is sufficiently small so that we can assume that the bulk concentrations and the temperature are quite well defined, and that we do have mixing effects, but they're really because of an increasing viscosity. Simply said, they're at the so-called micro scale. They are hidden inside the mixture. If you have something more that resembles water, you have that the diffusivity of the molecules is much better. If you then go to more spaghetti-like configuration at higher yield or higher conversion, you have diffusivity constraints for the longer chains and molecules. The modeling tool I would like to show today is so-called Kinetic Monte Carlo. But before going really into full detail, this slide, which is coming from, or this picture, sorry, from a recent review we have done, what are the ideal targets of a simulation? And if we keep dreaming a bit, then we would say we want to know how every molecule looks like. But this is a tremendous job, and like Markus said in the introduction, we need to do some sacrifices. But just to illustrate for the people less familiar with the field of polymer reaction engineering, let's just make a polymer only of chain length 3, 4, and 5, and even then you have already a large variety of possibilities. You see, for example, if you have a homopolymer or a copolymer, the difference between blue and orange units, there are quite some possibilities if you want to incorporate a certain functionality. And if you then allow even for small branches, you see that rapidly the number of combinations goes up, specifically that typically a polymer has like a chain length up to 1 million. These are just linear or loosely branched chains. We also have cross-linked systems, and then we have the question, how complex are the initial building blocks? In this case, we have something of functionality 4 that is clicking with something as well as functionality 4, but also there several patterns can take place. And if we zoom in a bit, you could have intermolecular reactions. So this means that two molecules that are separate do a click, but you could also have that because the molecule is already so rigid that two functional groups that seem to be at a certain distance, they are in the same molecule, and then you have a certain click. This has a strong impact on the polymer properties, and this is also something I would like to illustrate. So if you combine all this, knowing that the topology can vary, that the chain length can vary, that you have several comonomers present, at one point we need to somewhat computationally seek for a compromise. But I will show that with Monte Carlo simulations and some tricks, we can really already bring a lot of information from an industrial point of view to improve properties. To show that a bit, we first always need to ask ourselves, what is the target? You could say, I'm only interested in the average of a molar mass distribution or a molecular weight distribution, like depicted here at the bottom left. But typically we're a bit more, let's say, demanding, and we would like to have the full molecular weight distribution or molar mass distribution. And that shape tells us really something about the type of viscosity we have and the type of polymer. But many polymers are in practice copolymers, which means that it's not only the chain length or molar mass it's something we're interested in, but also the amount of one comonomer versus the other. In this case, a fraction of 0.5 implies that 50% of that chain length is with A and the other half is with B. But we see a quite dynamic shape and some off-spec of a couple of percentages. Even look, for example, in a contact lens, if you are a bit off-spec, you suddenly lose the performance that is desired. You can imagine that having two axes of independent variables, that makes the mathematical model much more complex. Another example is depicted here at the top middle. We have a simulation of a spectroscopic technique. We have that the mass over Z is different. We have the chain length being clearly visible, but there are slight variations because every chain has n groups, and these n groups can be different. And in that way, you could achieve a different overall molar mass. By having this type of fingerprinting, you have a better idea about the composition of the polymer. But the holy grail is really to look chain by chain how it looks. If you first zoom in at 2D format, we have something here at the bottom right. If you look at the previous presentation, there we had it on morphology. Here we zoom in and we try to have chain by chain information, simply said how the blue and the red units are connected with each other. The black is just background. You can imagine that this is just a snapshot to put it on a slide, but in practice, we need to track billions of those chains to be stochastically representative. And if we even push it a step further, we are not talking only about 2D representations and also branching levels, but we also go fully to 3D representation as function of synthesis time, what is happening in the reactor. But before we really go into full detail about what these modeling tools can do, let's start at the very beginning of so-called kinetic Monte Carlo simulations. I stress the word kinetic because they are time dependent and they take into account reaction probabilities. And what we have been doing at Ghent University is following the so-called Gillespie algorithm. I think we can say that Gillespie pioneered the field with, at first sight, a very basic algorithm, but it really, really works. Although we must admit that it was originally developed for more elementary systems, not really with macro species like in polymerization, simply said A goes to B, B goes to C, and so on. And what do you have? That the reaction probabilities determine which type of reaction takes place one at a time. So these simulations really discretely pinpoint which reaction needs to take place, taking into account reaction probabilities. But the toughness is really when you have chain length dependencies, because when you say I will execute a propagation reaction, the computer needs to decide which chain length is involved, or when it's a termination reaction, the two chain lengths that are involved. And you can imagine that if you would do it fully in full detail, every chain length pair has a different reactivity. You will have a tremendous amount of reaction channels or reactions, if you say it a bit more simple. So you need to have all kind of smart storage and search algorithms to make kinetic Monte Carlo applicable to the field of polymer reaction engineering. I would like to illustrate what we can do based on a case study, which is the synthesis here of a polybutyl acrylate. It's an important polymer in, for example, coating applications. To not overload the presentation today, I focus just on the homopolymer. But just to make clear, we can extend this also to copolymerization. What is so special about this type of polymerization? I stress we are at lab scale. This is a quite exothermic reaction, which means that even if you're doing a quite dedicated temperature control, unless you can go to a microreactor or you're very diluted, you will always have a temperature spike. And this makes the kinetic analysis more complex unless you go to a specialized technique like pulsed laser polymerization. But this is really in a flask, let's say the mini version of an industrial reactor. That's one thing which is special. The second thing is that there is not one dominant radical type, which is the conventional secondary end-chain radical, but there's also something like backbiting, which means that the secondary radical is transformed in a tertiary radical, which is more stable. That's the driving force. But if then propagates, you get a a small branch. But if you're at elevated temperature, you can also have beta scission, and a bit more in engineering style, beta scission to the left or beta scission to the right. You obtain in the end unsaturations, and these have an important impact on the behavior, but also allow for further modification. You can think about the coating application. So if you look at this process, you're interested in the chain length distribution, but you're also interested in how many double bonds you have and how many branches you have. Again, what Markus said at the beginning, we need to have distributed information. So without going too much into detail, we did a lot of parameter tuning. We did some model validation to experimental data, and then we tried to see what is the ideal cooling temperature to come to more or less an isothermal and safe polymerization. What is meant with that? Let's take the extreme case where we have no heat exchange, so there is an adiabatic condition. We see that the temperature more or less goes to the roof. This is a simulated runaway. Of course, the conversion is going quickly towards 1. You have a very short change because the temperature is so high that you have a dominant pathway towards beta scission, but at the end, it's not safe. You need to really apply a certain jacket temperature to force the system to achieve a safe environment. And in that way, you have a much slower polymerization. And indeed, you see that a mass average chain length or mass average molar mass is really behaving well. But in the end, you're interested also in the molecular weight distribution. Like I already said, when you have a higher temperature, you have more side reactions. And in this case, we see that for the lower temperatures, we have a more narrow molar mass distribution. But look, for example, at the black one, which was the adiabatic one, you clearly have a very broad distribution. I need to stress that this is the uncorrected simulation result versus experimental interpretation. So there is no sec broadening, but this is the pure contribution, for example, of the very short macromonomer that is formed here. On top of that, it's not only about molecular weight distribution, but it's also about other properties. And in that case, we have in this plot here at the middle, which is the relative contribution of macromonomers, so chains containing a double bond versus that polymer. First bar is on number basis, second bar is on mass basis. What we clearly see is when we have no cooling, that the contribution of macromonomer is huge, because we really are at high temperature, a lot of side reactions. But most importantly, we see a quite big scatter depending on the cooling profile that is being applied. And the same thing is true for the dispersity. The dispersity is, of course, which is the second column here, linked to this distribution. It's a measure of the broadness, but also the short chain branching distribution, the long chain branching distribution. We see that depending on the cooling degree, we will have a different level. To come a bit more in detail, these were data done in industrial format, so they are a bit normalized. In the end, what we would like to have is a very fast polymerization, but safe. And we would like to be able to make both a narrow and a broad distribution. If you focus on a reference case, which is the red line here, we clearly see that if you do the cooling at a too high temperature, you always will have an unsafe operation. So this is something that should be excluded. If you would like to make the broad distribution, which is the green line here, you can cool down, and at one point you can accelerate a bit, and you don't have a temperature spike, which is exaggerated. So this is a protocol, a safe protocol, allowing you to achieve the broad molecular weight distribution. If you would want to have a narrow molecular weight distribution, you really need to cool sufficiently to block the side reactions, and this is depicted here by the blue line. And you also see that different type of average molar masses are achieved together with different types of branching levels. Before I go to the second case study here, I would like to stress that in the end, when from an industrial point of view, you're interested in a certain batch time for a certain conversion, you're interested in a certain branching degree, a certain broadness of your distribution, and then you can pinpoint the most interesting protocol to apply to achieve this multi-response behavior. The second case study I would like to focus on has to do with a cross-linked system. So remember that in the beginning of my presentation, I said that there is a huge difference between linear or loosely branched systems and cross-linked systems. And you can imagine that when you have cross-linked systems, depending on the complexity of the building blocks, the overall connectivities become more complex. And this is illustrated here on the slide. We start with diamond, just to make clear, this is really a perfect organization, which gives rise to certain properties. If you then take silicas that are connected with each other, you have already a bit of chaos, but I think we all agree that this is quite ordered still. But if you then go to a typical hydrogel made by a free radical polymerization, you end up with a big mixture of a lot of species with different properties, and this is much more complex to be covered. How do we tackle that? Well, we need to have much more detailed software taken into account. We have initial molecules that are the building blocks. Just to make clear, we're talking about the case study here in the middle. We have building blocks that are connected with each other. We start to form the first macromolecules. We need to know the Arrhenius parameters. So how easily is temperature forcing a certain reaction over another reaction? I need to make a comment that these are reversible reactions. So we need to take into account both the forward and reverse one. But at one point you start to have macromolecules, and then I would say it becomes a bit more complicated because two molecules need to diffuse toward each other before the actual reaction can take place. And then molecules that are smaller or are in a less viscous environment, they can really undergo a fast diffusion. But if they are too rigid, they will not be able to do that. And on top of that, you can have that certain functional groups react with each other in the same molecule or between different molecules. Like I said, there is a difference between inter and intramolecular reactions. Look here at the red cross. This is in the same molecule, but the two molecules, functional groups are too far from each other. It will not happen. You could also have shielding, and that part of the molecule is overlapping or somewhat blocking the view of a certain functional group, and in that way, it's very difficult to get there. In the end, when you want to really understand in full detail how these network syntheses are going, you also need to know the 3D positioning of every individual building block. So you need to know the bond angles, you need to know the dihedral angles, you need to have a lot of information, and therefore we also have a link of our Monte Carlo simulations with molecular dynamic simulations. And in the end, once you have all those 3D positionings of all the individual molecules, you can come up with whatever distributed property that you're interested in. I will focus on that a bit later, but for example, you could say I'm interested in how many cross-linking points I have per molecule, but this will be a distributed property. And the final step is then to go to the performance and to try to understand how material properties are influenced by the distributed properties before. To go a bit more into detail on the steps from before, this is the basic reaction scheme. It's not everything. It's only showing the intermolecular reactions. You have a hydrolysis. You first need to bring the system to a sufficiently hydroxyl groups so you can do the condensation. But there it also begins. You have water condensation and you have alcohol condensation. We have done a lot of experiments, or we also looked at literature to tune these parameters more at the lower yield so that the diffusivity is less an issue. And then we further tuned our model, taking into account higher yield data. And this is the result depicted here on this slide. And so we have the small molecules at the start, our building blocks. We start to increase the yield. So we're making silicon, oxygen, silicon bridges. And you see that everything starts to flatten after a certain time because the system has become so rigid that further reaction is only by intramolecular clicking. And in the end, you are not able to come to 100% yield. More importantly, we take certain time steps, T1, T2, and T3, and we are really able to show, and this is only a couple of molecules, how the connectivity of the individual monomer units is taking place. And if you look carefully at these plots, you could say that at low yield or low times, this is still quite ordered, but if you go to a higher yield, it's very chaotic. And this makes us understand that we really need to have a lot of molecular information to go to very detailed structure property relationships. I said that we can always tap off certain properties, and I have at the bottom right 2 examples, namely how many chains in concentration format we have that have been cross-linked at least 3 times. We have seen that this is important to understand the strength, but if you go to really high yield, we also have seen that you need to know the fraction of intramolecular clicking. So these intramolecular clickages make the chains also entangle and create extra strength at high yield. And so once we have seen in experiments that you really need to push the system to very high yield to obtain a sufficiently strong material. And this has to do with majorly two things. You need to have sufficient amount of crosslinks per molecules, but you also need to have a sufficient amount of intramolecular linkages. You can even go further and you could say, let's really look at distributions like the cross-linking point distribution, again at these 3 time steps, just to give you an idea. If everything would be perfectly without intramolecular reactions, you have a much more open structure, which is much more, let's say, regulated. Compare this inset here with the picture you have here. This is much more chaotic, although still rather ordered. This is how it would be in the absence of intramolecular reactions. But the cross-linking points, 3 means that it has 3 crosslinks, so 3 arms that have grown, and 4 means that it are 4 arms that have grown. You clearly see that the time has a huge impact on this distribution. The same thing for the chain length distribution. In this case, the total amount of monomers that you have. And even more interestingly is the one here at the right. This is the molecular pore size distribution. So if you zoom in here, you see that there are molecular pores that are defined by the monomer units creating, let's say, the ring. And you can count this all with algorithms. And we clearly see, because of the competition of inter and intramolecular reactions, that you end up in the end with a quite a multimodal molecular pore size distribution. As I said, once you have those distributions, you would like to have a lot of information to link it to the performance of the material. And this is shown here on this slide. We have made membranes that are used for separating something which is hydrophobic and hydrophilic. You play with the functional groups that are on the membrane, and with playing with that, you're able to separate a certain stream more or less. And we have seen that by playing with the synthesis conditions, in this case, the initial ratio of water and the initial building block, the tails, we can really push the system from highly hydrophobic to highly hydrophilic. And we have seen that the simulations go much further than what experiment can do. A contact angle is something which is used in the field to address the hydrophilicity, but it's not sensitive enough for the very, very high amounts of hydroxyl groups. So you are not sure if you have fully functionalized your membrane in this case. And by doing our approach, we succeeded in that. And we really could put the filter rate efficiency at a very high level. This is all at a lab scale, and I briefly want to show that we're also working heavily on scale-up and industrial design. And so what I said before is a bit more this type of setup. We have a flask, we have quite good mixing, and then we try to understand what is happening here with the viscosity and also the individual chains. But in the end, we also would like to go to a continuous process, and we would also like to go to larger reactors. And in this case, we use our Monte Carlo platform in a compartment mode where we go compartment by compartment, depending on the configuration of the reactor. And we really follow again, molecule by molecule. I just want to show a brief case study where we aim at a polymer modification. It could be like the synthesis of a compatibilizer in the context of recycling, but you can also see this broader as mechanical recycling, where you have certain degradation taking place, or even chemical recycling because of the high temperatures that chains start to become smaller and to crack, and in the end form a product spectrum of oligomers and even monomers. In this case, you would like to graft a monomer on site the polymer backbone, but there is also a side pathway, which is the classical homopolymerization. What is the novelty here? That we're not only interested in having molecular distributed information, but also would like to have the resonance time distribution. We would like to know how long every molecule is staying in the reactor, in this case, in the extruder, and there is some forward and backward mixing. So not every molecule has the same resonance time. And this is what is depicted here. But slice per slice, we also have information on how the structure is looking. For simplicity, I only have shown a couple of molecules, but in the end, we have the full spectrum of every slice available compartment by compartment. And in that way, we can really lift Monte Carlo simulations to the industrial scale, also take into account the transition from, let's say, batch to continuous processes. So this brings me at the end of my presentation today. I've shown that kinetic Monte Carlo simulations really allow us to obtain very detailed molecular information. This is relevant for both synthesis, modification, and recycling involving polymers. We can really obtain very nice structure property relationships. I think in the polymer reaction engineering community, and it's not only at Ghent University, but also broader, we're really working on that. And also people in this talk presented today have made very nice contributions in that respect. I think we should keep continuing collaborating on that. And the last thing I've shown is that it's not only about lab scale, but it's also about process design and scale up and really going from batch to continuous. This brings me to a large slide with a lot of faces here. We have a lot of people being involved at Ghent University, but we also have beyond Ghent University collaborations, and specifically the silica work was done together with the group of Professor Darmstadt, and we have also some validation seen with the more network systems together with Professor Barnard colleague, but you see also other collaborators we have in the polymer reaction engineering community. They're not all listed, otherwise the slide would be too crowded. I can also highlight Dr. Pintlon, who is in lead of a spin-off related to the commercialization of the Monte Carlo tools that are available. And with this, I really want to thank the organizers again for giving me and Ghent University the platform to present our modeling approaches, and I'm willing to address questions if any are raised. Thank you.
Yeah, thanks a lot for this very nice presentation. And I think there's already one question in the Q&A tab. It's from Robin Hutchinson. He writes, a nice presentation. My question is about the butyl acrylate batch example. Scale up, especially from a safety perspective, seems difficult, and many companies turn to semi-batch staffed feed operation. Are there advantages in running in batch at larger scales compared to semi-batch?
Well, it's a very nice question from Robin. We have also, and I didn't include it in this presentation, performed the semi-batch simulations, and we have seen that these really help to scale up the possibilities, both in safety and also with respect to property control. So, in fact, if you really want to push it to larger reactor sizes, we need to take into account the semi-batch mode. If you would do it fully batch, then you have a much more limited range. Of course, it depends on what your targets are, but I would say that the combination of both temperature control and semi-batch feeding or star feed is the way to go in this perspective.
Yeah. Okay, thanks for your answer. I think that's definitely always something that we have to keep in mind when looking at simulations. It's one thing to start, for example, with a batch, but then there's always this step going to larger scales. Yeah, so with the sake of time, I think we can close the discussion here. If more questions arise, we will take them to the panel discussion, and we'll move on to the next presentation, which will be given by Petr Singstad from Cybernetica. We are very happy to have you here and give us a presentation. You are working in a company that is specialized on model predictive control, if I understand correctly. So we'll hopefully get some very interesting insights into how they can be applied to industrial examples. So Petr, the screen is yours. Looking forward to your presentation.
Thank you, Kristina. Can you now all see my screen?
Yes, that looks perfect.
Yeah, so let me start by introducing the company briefly. You already introduced the company. It's a control engineering company, and the topic of my presentation is nonlinear model predictive control of industrial semi-batch polymerization reactors. And this is a core business of the company, but let me just briefly review what we do. The company develops supervisory control systems, as in model predictive control, We do that for industrial processes, first of all, and our system has the ability to learn from plant data, adapt to changing process conditions, optimize the production, and do that in a way that we run the operation safely. And the business case of every such application is, of course, that it's cost effective in the end. So we do that for chemical industry, as we are talking about today, and the specialty is polymer application. But we also provide these systems for metal refining processes, for primary metal production, for aluminum electrolysis, for oil and gas applications, and most lately for amine-based CO2 capture plants. This is a pilot plan of the coast of Norway. The company has been in operation for 22 years now. So in 2 days, we cross 2,800 years of accumulated operation time for our systems running 24/7. There are 573 of them. We are right now having roughly 100 new applications in commissioning. They are spread over 4 continents and 11 countries. So that's briefly about the company. So the technology that we use and provide, and that I'm going to talk about today, is nonlinear model predictive control based on first principles models, which means that we have technology for using process model to improve process profitability and safety. So, and I guess that's the main takeaway from this presentation, that when people put a lot of effort into developing kinetic models of various polymerizations, this is a tool that one might use to put the results into practical operation in an industrial setting. Having said that, it's not just to take our software and plug in a model and then think that you have something running online. It's a bit more to it, and I'll go through that a little bit step by step right now. So I already introduced, this is the contents of what I'm going to talk about. I already introduced the company, so I skipped that point. Then I'll talk a little bit about the technology model predictive control, and I'll come to 2 examples. One from suspension PVC, which is a batch or semi-batch process, and a semi-batch unsaturated polyester polymerization. Let me go to the technology base. So it starts, the development of an NMPC starts with a model. I'm just trying to move my screen. I have some problems with that. Just okay. So it starts with a model, and let me start with an example model and a case that I'll get back to, which is semi-batch polymerization of suspension PVC. So this is a strongly exothermic process, but and the reactor kinetic models, we need to have a model that fits for the purpose of doing control. That means that we need a set of ordinary differential equations, or we might handle partial differential equations or differential algebraic equations too, but nevertheless it should be run fast and be suitable for the purpose of control. And in order to develop this model, and this is of course well known in this community, we need a kinetic model, In addition, we need some thermodynamics. In the case of SPVC, this is a free radical polymerization, where the molecular weight is mainly determined by chain transfer to monomer. In the thermodynamic reactions, we need to calculate phase equilibrium with the distribution of monomer between four phases: the water phase, the gas phase, and the polymer-rich phase, and the free monomer phase. And this is done by the Florey-Huggins equation that was mentioned by Juraj earlier today. And we need to calculate the volume of those phases. We need to calculate mass and heat transfer, mass transfer between the phases and heat transfer from the cooling system, for instance. We need to do some assumption on mixing, and we need to calculate some polymer properties. And of course, we need to model the cooling system with an energy balance, not only for the suspension, but also for the cooling medium on the jacket. And in this case, it's also overhead reflex condenser. So there will be three energy balance equations. Having developed a model, we have a set of differential equations, and we have a software that we can plug this model into. And this software is made to run on a server at plant. It could, of course, be in the cloud, but mostly we run it in a server at plant so that it can run in a safe network with firewalls to maintain safety of the cybersecurity. So the model read plant inputs, the same plant inputs that's put into the plant, and of course the model calculate the expected measurements. So this is step one in a model implementation online. It's of course not useful yet. In step two, we start to get something more useful, because then we take the discrepancy between the model measurements and the real measurements and run that through an estimator to correct the model and make sure that the model fits what's going on at the plant. And now we start to have some useful results perhaps, but we take this one step further, and we augment the model with some parameters. We assume that we have a good model, but we know that we never get a perfect model. So in order to make corrections, we do update not only the states of the model, which is the states of the differential equations, but also certain parameters that will make time varying. Let me illustrate that with an example from the same case with the SPVC, where we allow some parameters to vary with conversion, and also track them over drift over weeks and months. So we have a correction factor for the reaction rate. This is for a number of batches, and we can see here that our kinetic model is not perfect because we have a systematic variation over the duration of a batch. But as long as it's systematic, we can just use this correction and add it, augment it to the model, and we can make predictions based on this correction factor. And similarly, we can estimate the heat transfer coefficient for the cooling jacket. It ought to be constant, but we see that it's not entirely constant. And most likely, when we come to high conversion, we see that the viscosity limits the heat transfer, so that the model would overestimate the cooling. And with this correction, we can compensate for that when doing control. So these conversion-dependent parameters we use in batch optimization. And then we have the final step, and now we can start talking about control. We close the loop and facilitate feedback control by this controller. And the controller uses the same plant model as we use in the estimator. So to summarize this, we have two functionalities in this structure. One functionality that the estimator in combination with a reactor model that allows us to learn from the history, looking backwards in a way. And then we have the other functionality where we do the control, and the NMPC control action is done by looking forward. So we make predictions into the future, running the model, and then we do an optimization in order to define the best possible plant inputs so as to minimize optimization criteria. It's a bit simplified explanation, but let's leave it with that right now. And then I'll move to some examples of using this technology. And then come back to what I've used as an example already, the suspension PVC polymerization. In our technology here, we have two levels of control. First of all, we have the dynamic real-time optimization layer, and we have a nonlinear model predictive controller in addition to that. Both are implemented in the same software, but with very different focus. So the problem at hand here in suspension PVC polymerization is that we want to minimize reaction time and hit the correct product quality. So this process is highly exothermic. So the key solution in order to do this optimization is really to utilize the available cooling capacity as good as possible, and we do that with introducing non-isothermal polymerization. And at the same time, of course, we need to maintain this hit the thermal product quality. So here's an illustration of the control hierarchy. At the top layer, we do a dynamic optimization where we optimize the whole batch, and we redo the optimization. So we optimize the remainder of the batch once the batch has started, and we typically redo this optimization every 5 minutes or something like that over the duration of the batch. And then this optimization gives us the optimal temperature profile for the reactor and also the initiator dosing. And that's sent to the next level, which is the nonlinear model predictive controller, where we set up that to track the temperature profile accurately so that we, in the end, produce the polymer that we want. Yeah, so some results from first from the estimation. Here we estimate the heat transfer for the jacket and for the reflux condenser, and we see that it's not constant, it varies through the batch. I'm not able to explain exactly why it varies like that, but it's repeatable, and we use that information in the optimization. We both use the information from the current batch and also from previous batches in order to do the predictions. And then we have our reaction rate corrector, and we see that our kinetic model is not perfect. We need some adaptation in order to make good predictions with it. And also when it comes to our thermodynamic calculations, we see that especially after 60–70%, when the free VCM has disappeared, our equilibrium model is not good enough, so we need to do a correction there. So here is some optimization results from this SPVC case. We optimize the reactor temperature, which you can see here. And in this case, it's a rather high temperature product. So then I don't show the temperature scale here. I'm not allowed to, but it's a relatively high temperature. Then it's optimal to keep increasing the temperature. If you had a bit lower temperature, it would have been more optimal to start higher and then have a more U shape of the result. But all that comes out of this optimization. In the same figure, I show the pressure, and we see here we have a constraint on the pressure for some period of time, while the reactor temperature is increased throughout the batch. Here we have the initiator profile. We see that we have a large initial initiator dosing, but we also optimize a few additional doses through the batch, and we calculate the remaining active part of the initiator in the model. Here we have the conversion, and we have the target conversion, which is a bit less than 100%, and we can calculate when we hit that. And of course, that's a critical time for minimizing that time makes money to the producer. And then we also have a terminal quality specification, and we see that in this case we hit that terminal quality at the time where we end the batch. So my second case was unsaturated polyester process, and the objective here is to more or less exactly the same. It's to minimize reaction time and hit correct product quality in the end. But the mechanisms to reach that optimal solution is very different. This process is not exothermic, so cooling capacity is not an issue. This is an equilibrium reaction, and the clue is to remove water, reaction product, to drive the equilibrium to high conversion. And that's of course seen in the design of the process. The control challenge here lies in the complexity, the high interaction, and highly nonlinear process performance. So in the process design, we see here that we have a reactor, we have a column to separate water and to feed back the glycol monomer. And we have a reflux drum, a condenser, and we have a vacuum pump. And the challenge is, of course, to hit the terminal quality as a challenge in itself. The biggest challenge is the high interaction between the column and the reactor. It's a difficult process to control, and also it's a challenge to avoid loss of glycol over the top of the column. So here we have 4 variables to manipulate: the temperature of the jacket, the reflux from flow to the column, the pressure on the top of the column, and the dosing of glycol. It could be feedback from the tank, but it could also be fresh glycol, of course. So here are some results from that. I'm coming to the end. We see that early in the batch sequence, it's a key here is to avoid abrupt variation in the water evaporation rate. So here we ramp up to a target reactor temperature, and we have limitation in the ramp up, and it's constrained by the predicted evaporation rate, so that we don't flood the column, and so that we can balance the column with a reflux to ensure good separation also early when we start producing the water. So the next slide is from later in the batch. Now we have more or less reached the target temperature, but now we try to drive off the water, and we optimize or we try to drive out the water by reducing the pressure, but we constrain the pressure by predicted load of the column again. So here's the column is a restriction on how fast we can do this and drive away the water. And at the same time, we drive the equilibrium to the right in order to maximize production, of course. And once again, the reflux is controlled to optimize separation in the column. And finally, here is a slide showing the hydroxyl number and the acid number towards the end of the batch. And we see that we hit the target both in both numbers at the end. So to summarize this, I have tried to illustrate that nonlinear model predictive control technology offers possibility for increased profitability on polymer production, and that we can ensure consistent and correct product quality. And our company make that into a business. So we have a software called Cybernetica Zenit, which is proven and which we have applied to these kind of applications for many years. We do a turnkey installation in the company. We have a full maintenance program, and we do offer installations almost worldwide. So my last slide is just my business card, and I'm happy to answer questions.
Thanks a lot for the wonderful presentation. And we already do have a first question, so I would pass that on right away. The question is from Klaus-Dieter Hungenberg, and he asks, target polymer properties are usually endpoint properties. Is there any information on how different reaction pathways caused by the controller optimizer influence application properties?
I guess that Klaus knows more about that than I do, but in general, the answer is yes. In these two examples, it's not that complicated.
Okay.
Yeah. But there are examples where that could be the case, of course. But we have limited experience with that in particular.
Okay, so there's the next question from Joao Bordado. He asks, how do you input the glycol loss?
How I input it?
Mm-hmm. I'm not sure if he means the model or how it's implemented in there.
No,
Maybe
there is, of course, yes, there is. We try to estimate the loss of glycol over top, but that's done by.
What type of sensor he has added now? So I guess the question is more on the experimental side.
Yeah, right. So what I can say is that we have some updates from sensors, and we do model calculations on that. Of course, so the model predicts that, and we correct the models from either from sensors and from sensor grabbing. When it comes to the sensor techniques, I'm not an expert on that, and I'm not at liberty to say much more about that.
Okay. So I think we are then perfectly on time. So I would like to thank you again for this really nice presentation. Very impressive examples that you showed. And then we could move on to the next presentation, which will be given by John Tsavalas from the University of New Hampshire in the USA. Perfect. You're already starting your screen sharing. So John will talk about emulsion polymerizations, and he will focus on the chemistry, but also on process dynamics, and if I understand correctly, also on diffusion limitations. So I'm looking forward to the presentation. John, the screen is yours.
Thank you so much, Kristina and Markus, for the kind invitation, and good afternoon to you all. It's morning here, but still light. Can you hear me okay?
Yes, perfectly.
Okay, great. This is the laser pointer. Okay. So today I'd like to highlight some of the competition that we can observe in emulsion polymerization between the chemistry of the reactions that are occurring and the influence of process dynamics. I think we're all well aware of the adage that emulsion polymers are a product of process, and I intend to show some examples of that here today. First of all, I just wanted to say that we are here on the East Coast, about an hour north of Boston at the University of New Hampshire. We've enjoyed a wonderful fall season, turning of leaf colors, which has been beautiful. Now we are nearing the time when everything is white, but I think we all experience that soon. And just as a brief overview, my research group is dominated by polymer reaction engineering, but confined within the colloidal space of emulsion polymerization particles. In order to assess how to guide the morphology of multiple phases in the confines of these particles, we need to understand things in multiple scales. We need to understand the influence of molecular structure, polymerization conditions that would lead to macromolecular architecture changes from linear polymer to branch polymer to networked polymer, because largely these types of things all influence how and when a chain is able to diffuse. And in order to achieve interesting particle morphologies, diffusion is critical to be able to move them to different spatial locations. We also do take the particles and look at how they assemble into larger macrostructures, but I won't be talking about that today. The only other thing I'll say on this screen is that most of our polymers are, of course, dispersed in water. So the influence of water on polymer properties is another crucial factor to take into account. Here are some non-spherical particles that we've been developing lately. I don't have time to go into today, but in order to get to these rather uniform valencies of lobes, diffusion is once again the critical factor to deal with. These asymmetric particles are also a product of controlling diffusion at different points in a reaction. I also am really enamored with these particles as I'm Greek of origin. These remind me of nanosheep. But lastly, I'll say, as an example of colloidal environments that we work on, we've also been now understanding how to take spherical particles and elongate them into these spherocylindrical structures, which in fact you can't see in this image. These are actually also hollow. But in order to control morphology, there are quite a few factors one has to account for. And of course, one of the things that I want to highlight here is how do we model these things? How do we try and understand the fundamental mechanisms that drive these different morphologies, shape, or distribution of phases? And it's a very complex endeavor, even for a single homogeneous composition. So as one last example of experimental distribution of two phases, chemistry makes a big impact, right? If we don't choose or there is an impact of the choice of monomer and structures that we use on how they can move and rearrange, both from thermodynamic and kinetic and diffusion perspectives. In these two images, the system is largely the same. The black stained phase is polystyrene. The unstained phase, white, if you will, or light gray, is a copolymer of methyl acrylate and methyl methacrylate. But varying the TG of the acrylic phase by changing the ratio to either favor MMA or to favor methyl acrylate, can influence their TGs, and the diffusion of the second stage of styrene, as is polymerizing in the presence of that seed, can be impacted by that TG. But what I wanted to say was, we don't have to change TG, we can change process condition. These two images look like completely different systems. In fact, they are, again, the same polystyrene and polymethyl co-methyl methacrylate. The only difference here was this was done on the left and as a batch reaction, and this on the right was done as a semi-batch reaction, restricting the entry of the second stage into the seed. So there's a dramatic impact of process control. This is just one example. And beyond this, there's another way that we can, not just TG, that we can influence the ability for chains to diffuse, and that's with cross-linking. Film formation for coatings is quite important to be able to coat the surface, but we want that film, once prepared, to be durable and lasting. So we have tools with us to understand how we can modulate TG. We can lower the TG for film formation with plasticizers, but then we contend with those maybe persisting or influencing the long-term properties of the coating. And another way is to engage cross-linking after film formation, or even at the right time during film formation. So this leads us to how can we predict when cross-linking will happen, and how do we guide those choices and mechanisms to be controlled both by reactant choice and by process conditions, for example, mode of addition of the monomer. So network topology is quite important, and diffusion is really can override thermodynamic factors quite greatly in this example. And if I use the classic de Gennes model of reptation of a polymer chain through a tube-like free volume region, it's very easy to see that if this red reptating chain were to have any branches in it or full crosslinks, it certainly won't be able to fit or move through that tube anymore. So it's really critical to know when does cross-linking happen. And of course, this is a function of kinetics. So I'm going to lead us into how do we search for rate constants that are effective in predicting and modeling the occurrence of cross-linking and the amount of cross-linking in a particular system. But when it occurs is actually the most important. So a lot of the cross-linking reaction can be covered by leveraging things that we already do for diffusion reactions, for example, termination reactions. So there are various forms of this type of equation, the rate constant for termination, having chemical contribution as well as diffusion contribution. But just to simplify in a pictorial sense, if we have a chain end radical, the gray area is the radius that it's sweeping, and we have another chain that these two red and blue radicals would like to terminate, they're not only going to have a certain reactivity, but they're going to have to be diffused so that their sweeping volumes are overlapping each other to some extent. Then we also have to say with cross-linkers, they're usually not the dominant monomer. So how are they spaced through the chain? And when are they incorporated into the chain? In fact, if we think about a cross-linker monomer, once it's incorporated into the chain, that actually becomes a macromonomer itself, having a pendant reactive group, but carrying this large molecule with it. So we have to contend with that as a completely different species than the monomer, the small monomer version of it itself. So if we look at a monovinyl, of course, we only have one chance to incorporate into the chain. But if we look at a divinyl, we need to contend with potentially, or at least from a modeling perspective, capturing different rate coefficients for the first addition and the second addition in a copolymerization reaction. So how do we account, or how do we measure, predict, or leverage the difference in reactivity of those two vinyl bonds? And cross-linking can happen quite early. So these are molecular weight distributions modeled for methyl methacrylate in black alone. and with 1% ethylene glycol dimethacrylate copolymerized with it in red. And if we move up through conversion, you can see that already only at about 5% conversion in the red profile, we're already starting to generate quite large molecular weight because we've started the cross-linking reaction. And this very rapidly starts consuming the rest of the linear chains to where the system is dominated by a very large non-diffusing, is the key point, molecule, where we still, of course, do have some linear chains left. So from a kinetic perspective, how can we capture that? Well, we use the same kind of approach that we talked about with diffusion in termination reactions, but now the pendant comonomer cross-linking monomers, we have to consider their own sweeping radius. The whole molecule has to diffuse, and that's captured in the diffusion coefficients, but the radius of termination for a pendant molecule is much smaller than if it were a chain end. So we look to structure of those pendant groups. And if we look at a very short rigid pendant group, like what would be from divinyl benzene, we can see that that radius of termination would be quite small and rigid. If we use ethylene glycol dimethacrylate, we have more degrees of freedom. The vinyl is farther from the backbone and has a more flexible spacer unit, which we can even increase if we increase that N-alkyl chain length in between the two vinyls with, for example, 1,4-butane-diol dimethacrylate. So we embarked on a study experimentally and trying to determine how do we capture these ultimately to determine a rate coefficient to leverage for that second vinyl. And I will simply say that we were able to leverage the initial reactivity rate coefficient as a monomer. And in this case, these are, fairly standard methacrylic monomers, but modified for its second vinyl bond by this parameter that we've called psi. In fact, the psi Greek letter looks almost like a branch, so that's why we leverage that. But how do we calculate this psi, or how do we experimentally determine this psi for different monomers? We have to look to kinetics. So here we're doing bulk polymerizations to capture the rate coefficient, where the blue curve is without any cross-linker. So this is the kinetics of a methyl methacrylate polymerization bulk alone. But you can see when we add cross-linker, we have a dramatic boost in the kinetics. Why is that? Why is there such a dramatic boost? Well, if we just look from a general perspective at the general rate equation, we have the propagation rate coefficient, radical concentration, and monomer concentration. Well, if we have cross-linker and we hypothetically activate each of these pendant groups, in a sense, we have a higher radical concentration, which should increase rate. But that itself is not really the dominant fact. The dominant fact is once we start cross-linking, we have a species that is effectively not diffusing anymore. So not only does it have a higher number of radicals, it has much slower moving chains, which means that they don't terminate as fast. And both of those factors contribute to this rapid increase in kinetics. But that increase in kinetics is something we can use to pull out that psi parameter. So we go both to differential scanning calorimetry, as well as to larger volumes to be able to measure gel and swell ratios for networks. And I'll say that we take the area under the curve of heat flow from differential scanning calorimetry reactions and effectively leverage that heat of reaction to develop our kinetic profiles. And then when we have an actual set of data, we vary that psi parameter. If I can just show it one more time. We vary that psi parameter in our models until we see which one actually fits the experimental data nicely, minimizing the error between that. And we can determine a psi for a particular system. So we did this. We did this for a variety of monomer pairs. This is methyl methacrylate with ethylene glycol dimethacrylate. One interesting thing to point out here is it doesn't matter the concentration. So for this 1%, 3%, or 5%, we used exactly the same psi parameter. and the dotted lines are our simulated lines. You can see how nicely they match. But what we then found was it's important the size of the monomer adjacent to the pendant vinyl. So if it's a small monomer like methyl methacrylate, this pendant vinyl has more degrees of freedom to move, compared to if there's a large monomer sterically next to it, it has less degrees of freedom to move. So we can see this captured in the various psi parameters decreasing as we get larger obstructing neighbors to that pendant vinyl. We then started turning to molecular dynamics to try and see how can we describe the accessible volume from a purely physical point of view. And the black entity you see there is ethylene glycol dimethacrylate. The rest of them are methyl methacrylate monomers. And I'm going to turn my pointer off for 1 second so I can move us over to here, where you see we let this run for quite a while and calculated over a period of time how often was that vinyl obstructed. And when we put it back and plot the whole data, we can see this in a three-dimensional plot, how often the vinyl was obstructed. And for a system where we had a small neighbor, the vinyl was able to sweep a much larger volume than if it had a larger neighbor. And this, at least in trend, followed these psi parameter evaluations that we pulled from the experimental data. So we extended our set to much longer monovinyls as well as much longer divinyls. And interestingly, we wondered if we could have something so large next to the vinyl that it might even block the accessibility completely. Could we shut off cross-linking due to the size of the neighboring group? I won't go through the details of the numbers, but you can see that we capture quite a wide range of these conditions. And I'll show you the final plot here. And we found something interesting in this profile. The y-axis here is the psi parameter. And the first set of work I showed you was a steadily decreasing psi for larger and larger neighbors. And that was this first drop in slope. But as the neighbors got longer and longer, the system kind of plateaued until a point where it had a precipitous drop to a much lower psi value, non-zero, but a much lower psi value, which then afterwards didn't really change anymore. We thought that was quite interesting. And there are somewhat three sections in this plot. And what will, for the sake of time, I'll just skip to it. If we have a very short, we can think of a persistence length in a sense, but if we have a very short distance between the monomer incorporated into the backbone and the pendant group, any new addition of monomer will effectively make a significantly longer, but in one dimension chain. But once that spacing chain becomes long enough, it can start to take on new conformations and shift to something that's more three-dimensional, like a sphere. Once we have a sphere, new addition in chain length is not going to make much difference in radius at all because of the radius cube relationship. So from 6 to almost 12, we didn't really see any change in the accessibility of that vinyl because it's effectively sweeping exactly the same area. So that's how we describe these all being roughly the same in that region. We shift from almost two-dimensional to a three-dimensional relationship with adding another unit to a pendant sidechain. There are other factors we can consider, which are if the pendant group is even long enough, it may even restrict some of the accessibility of an incoming radical to access that chain. So not only the receiving end, but also the giving end can be affected by the pendant length of the alkyl chain, should it be flexible enough. But I want to take this opportunity to say all of that was methacrylate. So these are all statistically incorporated copolymers. If we shift to now reactivity ratio, this is still chemistry, right? We can see a dramatic impact. So if we have, instead of diacrylates, if a dimethacrylate, if we have a methacrylic monomer with a diacrylate, they will have different reactivity ratios, and the cross-linker itself might be favored for incorporation early or favored for incorporation late, depending on reactivity ratio. And I'll tell you quickly that this makes a large difference. So if we look at a classic Mayer-Lewis plot for copolymers in our field are generally incorporated at less than 1%, small amounts. So we're really only going to be looking at this very top portion of the curve. And if I zoom into there, we can see that there are quite a few, even should there be large deviations at lower or larger concentrations, when we're way up here, many of these compress to almost 1-to-1 reactivity ratio, but some of them are off ratio. So the methacrylate acrylate is a little bit of a positive deviation, and the methacrylate styrene is a more significant negative deviation. And that apparently has a quite large impact on the kinetics, or we should say the accessibility and effective use of those pendant vinyls. So butyl methacrylate alone, we're back to bulk here, is this teal curve, the kinetics. And you can see for the same amount of crosslinker, just changing the crosslinker type with that methacrylate had a dramatic impact on kinetics, which in sense means a dramatic impact on the utility of that pendant double bond. What's quite interesting though, and we can do this in equimolar conditions as well, it's the same trend. If we look at those C parameters I was telling you about, the dimethacrylate and the diacrylate should have been much more effective at being utilized compared to this very short, rigid divinyl benzene. But if you look at the kinetic curve, the divinyl benzene had the fastest kinetics, which suggests the most cross-linking. And why is that? It's because from reactivity ratios, it was actually, compared to the methacrylate, incorporated much earlier. So once the vinyl is used, again, if you go back to the earlier slides, we have a non-moving molecule, effectively, a large, much larger molecule that won't terminate. That leads to accumulation of more chains that are not terminating, and unless they form a network structure. So just very quickly, I'll show another example. If we have styrene as the backbone and the same variations in monomers, we again get a boost in kinetics. But interestingly, in this case, for 1 weight %, we landed on the condition where all those C parameters ended up being, the reactivity ratio versus C parameter ended up having exactly the same kinetics. Styrene divinyl benzene has the most rigid dependent groups. It's just essentially one vinyl sticking out of a very rigid environment. But this takes us to the point that I wanted to make. We've spent a lot of time on the role of chemistry, the physical access of the reactive bond and the reactivity of that bond itself. But here's where process can override all of that. So the question we had is C sensitive to things like process conditions, monomer feed rate, or the amount of residual monomer, unreacted monomer present at any point in time? And we explored this with one system. So we have N-butyl methacrylate copolymerized with ethylene glycol dimethacrylate. And the only thing we did differently here was the time that we allowed for feeding of the monomer. And with that time difference, if you look at gel fraction, we have a dramatically different network structure that evolved from all the same chemistry. So if we did a very fast feed rate batch to half an hour feed, we get very high gel fraction. But the slower the monomer feed rate, the more pronounced we saw a drop in gel fraction. Star fed, in this case, led to lower gel. And why is that? In fact, I should also highlight here, we collaborated with Wei Gao of Dow Chemical, who did some molecular weight analysis for us for the crosslink samples by A4F. To exemplify this further, these were all linear feed rates, but we tried to see the impact of monomer concentration via nonlinear feed profiles. For example, fast followed by slow, or in orange, slow followed by fast, or a mixture of slow, fast, slow in terms of feed rates. And if you look at the corresponding gel fraction evolution, they took on a very similar structure. But a key thing in that structure of this profile, this is now gel content versus time. When the feed rate was slow, then we had actually quite a slow evolution of gel. But the minute the feed rate increased, we got a rapid generation of gel. So excess monomer aided in gel formation. Strangely, that's almost exactly the opposite to how we normally think of branching reactions. And why is that? So during a fast monomer feed, chain end propagation is dominating as usual, but in slow monomer feed, monomer concentration is very low. And what we mean by that is that free N-butyl methacrylate monomer is at low concentration. But if we have a chain end molecule that's a divinyl, that chain end is also a monomer. It's a macromonomer. And if that chain end monomer actually has an intramolecular reaction with its own divinyl, we can close that loop and continue the radical polymerization. But now we've removed a site of potential cross-linking from the pot. So we wondered about this particular intramolecular opportunity with divinyl cross-linkers, only those structures that are able to, and this we explored with ethylene glycol dimethacrylate. And we find an important thing. If we have a very low concentration of cross-linker, at slow monomer feed, if we generate a lot of these loops, because we don't have many other free monomers to react with, then we remove or severely limit the number of pendant vinyls available to form cross-linking reactions. Whereas this will still happen with faster monomer feed, but with faster monomer feed, there are also many other monomers available to chain end propagate, and thus many more of a larger fraction of these pendant vinyls will survive, allowing for downstream in the reaction more utilization to develop a tighter cross-link density and higher gel fraction. So we probe this with modeling, with the only change being the incorporation of that intramolecular chain end self-biting, if you will, reaction. And in the red dash, the black dots are the experimental gel fractions for, on the left, a fast, slow feed, on the middle, a slow, fast feed, and then on the right, a slow, fast, slow feed. And the red is the simulation if we don't account for that intramolecular, but we do account for the psi parameter that we talked about earlier. And you see that the red simulation does not fit the black dot data, but only accounting for adding that one more reaction possibility. And in this particular case, we found that first order rate coefficient to be an inverse seconds 4,000. You see that that reaction seemed to dominate, and even in these nonlinear profiles followed the experiment quite nicely. So with that, I'll just say that modeling affords a window into complex mixtures to help understand not only chemical contributions, but also process contributions to mechanisms. And with that, I'd like to thank Kristina and Markus again, and my co-authors Amit Chung and Yun Chung on this work, Wei Gao as a collaborator, and the UNH Latex Morphology Industrial Consortium. I thank you for your time.
Thanks a lot, John, for this really interesting presentation and the insights that we could get. So there's one question from Robin Hutchinson. Are you able to do measurements of gel content or analyze soil molecular weights to supplement your batch kinetic studies? And actually, I have an add-on, a personal add-on. Can you also measure potentially somehow the rings?
Yes, great questions both. So to Robin's question first, Wei Gao at Dow Chemical helped us to do these asymmetric field flow fractionization, A and a lot of F's after it, measurement. And the advantage of that is that you're not doing any, for those of you that don't know, I'm sure many of you do know this, but the advantage there is that you're looking at the whole molecular weight distribution. We're not solubilizing one fraction and trying to separate them. We're looking at the whole molecular weight distribution. For the data that I showed, we actually, for all the samples, we did the A4F, but we also compared it to our normal solvent-based gel fraction techniques. And they matched really quite nicely, but I'll honestly say that we trusted the A4F to a much greater degree. We can always fall into pitfalls with solvent-based extractions. So we were encouraged by that, but Kristina, your question of how about measuring the actual occurrence of those little micro loops? That is something that we certainly would like to have better quality analysis on. We have been trying to do some NMR studies for that, but this is a very small fraction of the mass that's in the system. And we're still working on it, but if anyone has any suggestions of a great way to characterize those micro loops with a quantitative confidence, that would be very welcome. But yeah, that is something that we do need to do to really corroborate our interpretation.
All right, thanks a lot for answering the questions. So I think, yeah, thank you again, John, for your presentation.
Yeah, thank you very much. And all of our speakers are back on stage, which is very good. And for the community, this is a very good opportunity to place some question in general to our speakers. So if there are some, we are happy to take them. If not, maybe we can spend a little bit time on two aspects. One aspect I think we may discuss together is modeling helps us understanding deeper these complex interaction of the behavior of these systems and controlling these systems. But the questions all of us simulation guys we are facing is about what about the real reactors and how close is the description? And what about the modeling status? How much of this is really implemented in industry? And maybe the speakers can give individual statements on that so that the audience, and I looked through the names, I found quite a number of students among them, so they might be interested. Peter, you have a modeling company, so maybe you start.
Yeah, we are two Peters there, but I guess
Oh,
you
sorry for that. The one with the two E's.
I'm not an expert. I'm passing it to you. I'm not Julius.
Okay, yeah. So so we are a modeling company, but also mostly a control engineering company. So this is a very key question for me, of course. So one point is the assumption that you made up front that once we have done a lot of modeling work, we should of course try to use that online or if in operation. So what we can do is a tiny part of that because we do use kinetic models in control. The state of the art is still so that the most high fidelity models we do not use. We as I tried to explain, we try to keep the models fairly simple and use data-driven techniques in order to compensate for the modeling errors and faults and so on. So one side of that is we should of course encourage people to continue doing modeling, and we are very open for cooperation when it comes to bringing that into use in terms of control and online optimization. But of course, there are other ways of using modeling in the industry. So other people could add on to what I just said, I guess.
Yeah, maybe. So you talked about high fidelity. For high fidelity models, maybe Dagmar can put an academic point of view on stage.
Yes, I think high fidelity is a broad term. I think from an industrial point of view, we need to identify what are the responses we're most interested in, and then we need to train the model to reliably obtain, so with high fidelity, the experimental data recording, and then indeed we need to do the proper model reduction translation. I think when I look at my presentation, which was focused around Monte Carlo, if you would set like 20 years ago that we would be able to go in that level of detail, I think a lot of people would have said very unlikely, to say it in a stochastic term. I think many of the PRE groups have already shown that we can do a lot of things. I think we also, with computer sources going up and a lot of developments in the fields that are purely informatics, we can do much more and more. So I think we need to keep pushing these high fidelity models and then do the proper model reduction. But I'm convinced that in the next decade, the model reduction can be done with even more advanced models, so that we're not really have, I would say, the essence or the conversion profile to be simply saying something. I really believe that this will be possible in the future. And if I can add something, I strongly believe, but by joining, in fact, the progress in the experimental field and the modeling field, that's really also something we need to work on. And then in academia, push, I would say, always to an even larger level of detail. If you look at the talk of John, for example, where we really go very in detail how groups are moving, that helps us to understand better diffusivity, but we can use a basic diffusion model then to go in a model reduction case. So I think the bottom matches is academia needs to keep pushing to go further and further. And I think industry needs to follow slowly, but of course, always in view of what are the responses we're really interested in. And I think we also have shown recently that the macroscopic properties, if you really want to understand them, like Markus said at the intro, we need to have something of distributed information there, and we need to go a bit beyond only having the most elementary averages. That's a bit my point of view.
Yeah, thank you. Juraj, you do a lot of modeling, really going from the essentials and from the fundamentals, and not only on forms, on static loads and formation and structure. So what would be your perspective in terms of universality and of the utilization of the models?
Thank you for the question. My opinion is that there is really not a simple sentence or statement how you can generalize what model is actually needed and so on. It's such a broad, diverse field, even what we've seen today. Sometimes the company, if you just improve thermodynamic prediction of some sorption, they are happy because they are producing millions and millions of tons of polymers, and so it affects many really industrial reactors, and any improvement in only thermodynamics helps. Of course, we can model not just the kinetics of the polymerization. Nowadays, with the hybrid Monte Carlo and fast Monte Carlo approaches, we can do a modeling of entire batch or semi-batch process in emulsion polymerization, including the Monte Carlo prediction of a single particle, let's say, in 2 or 3 seconds. So we are no longer restricted just to the method of moments, which were, of course, popular in the 80s when computers were slow. So nowadays, including branching and so on, we can really put 10 to 10 monomers within 3 seconds to some not statistically completely representative but meaningful predictions. Of course, we can address also what we've seen in the last presentation, which was, in my view, absolutely famous, absolutely fantastic coagulation phenomena. That means particle-particle interaction in the strong shearing, growth of the viscosity, and so on. All these dynamic equilibrium in between agglomeration and all these interplay. Again, it's a nowadays standard tool of many modeling techniques. So the modeling is such a diverse field, not just the core of the polymerization kinetics, but all the effect around that. I strongly encourage anybody who wants to do modeling, that it's fantastic course learning and comparing to experiments, and you are going to new areas of physical science, physics, chemistry, colloid science, and so on. So it's really, in what we see today, it was a very diverse field of what people are doing and how are they doing.
Yeah, Kristina, you're watching the chat and the any input, any questions from the crowd?
So far not.
So far not. Okay, nobody is daring. So then I throw another thing on the stage. So circularity and sustainability is a big topic, and I think specifically due to the production numbers of plastics, I think this is an important and a growing topic, and I think we cannot avoid that or pass by. I think you realize that in academia, on many conferences and activities, but also in industry, as there are strong efforts. So what I would like to ask you is to share your, on the one hand, your vision. So what would be your wish? So if you can define where to go from circularity on. And what about the strategies? What do you see for strategies to get polymers better compatible with circularity and sustainability? So anyone who dares to comment on that? Yeah, Dagmar.
So I mentioned during my presentation a part on polymer synthesis and a part more on recycling. I think one of the things we really need to do as a community is what we have learned for synthesis, also apply it for recycling. One of my key messages was try to understand molecule by molecule what is happening. And if you really want to understand degradation, either undesired or desired, you need to have some knowledge of the synthesis. And that's already a very big step. I think we also have a twofold task. On the one hand, with the waste that is there, to do something with that, but at the same time make new polymers that have a better durability. But again, my strategy would be to really do this in a teamwork, because we really need a lot of disciplines. But at the same time, if I look at it a bit more from my perspective and my career and what we have been doing, both in the university and in the spin-off, is to put the molecular scale really in it, and also convince people that if you want to steer the properties, and the recyclability is one property, you need to have some knowledge of that as well. That's a bit my first answer, I would say.
Mm-hmm. You're nodding.
Yes, of course. I have quite a lot of experience nowadays in some also semi-commercial projects on recycling. First of all, there are many degrees. Of course, the deepest one is go all the way to pyrolysis and again put the polymer together, which is so energy intensive that it's a question whether it really makes sense. The simplest one are, of course, the reuse, and in between we have a mechanical recycling, solvent-based recycling, and all the techniques. Of course, we have to live with the polymers that are today. That means mostly polyolefins, of course, not the ones popular that contain chlorine. All these polymers typically contain number of additives, dyes, and so on. So even by extraction of the additives, which is typically a very simple process with so many varieties, you can really get almost pure virgin polymer that you can put to the extruder and reuse again. Of course, by extruder, you are degrading the molecular weight. So then, of course, we may apply some either extraction of low molecular weight content, which is again not that difficult with many polymers, or a fractionation, not in the sense as we are used as analytical instrument or so on, but really on an engineering way, and we can again do a fractionation in many different ways. And there are many companies, and one of the strategies that of course works perfectly is this idea: let's put invisible mark to plastic parts that will be visible maybe on UV light, and that will help us in the sorting of the plastic materials. Of course, it will work only with certain products, not with the granular plastic waste from the cities. That means it's one of the most difficult area to recycle, but with many other products it will help. So again, it's a very diverse, broad field with many different strategies, and actually both big companies and small companies are already there, and academic community is just talking about need to do it, and the same politicians, but the companies are far ahead, at least 10 years ahead than most academics are in this field.
Yeah,
that's my opinion.
Yeah, this is also something I observe, at least for the large quantity products, that the companies they're going in there with a lot of efforts on a larger scale, so that that academics has even problems to keep pace. That's a way. What you are reminding us, or what you're mentioning, is another aspect on a community. We had it. Getting info or into discussion with people with existing recycling systems. And one comment from person from the battery business was, or a recommendation was, get your back streams under control, so that we don't get back a mess, but that we get back better control streams in terms of quantity and quality, so that we can do something with this. But Petr, maybe you have also a comment.
I'm really not involved in recycling for the time being. That's of course going to be a big miss, so I'm very eager to learn. But right now I just listen and nod.
Okay, good. Then I'm looking to the young generation. So Mariana and Kristina, you're the generation who has to deal with what we leave behind us and leave for you. Any comments from your side?
Yeah. So I think a lot of the important aspects have already been mentioned so far. So I think yes, there's an enormous need for action, but like you said, industry is already active, but there are still fields that we also in academia can tackle, especially when it comes to proving concepts, helping understand in detail, like Dagmar said, what is happening on both sides. So I think these are the challenges that we are facing, and that will have to be tackled. But I'm actually currently giving a lecture which is also dealing with circular economy, focusing on plastics. And the great thing there is that the students are really, really eager not only to learn what is the current status, but also to get involved. So I think that's the, let's say, the positive outlook that we have. That we have a lot of young people motivated and willing to contribute. Like you said, I'm also still young, so I think we can do our best to get circular and avoid plastic waste where possible.
So many eager hands to help. So Mariana unmuted.
Yes. Well, actually, I am really happy to see that in the work that I'm in the lab that I am working, and also myself, like I'm starting to see like in the young generation that aspect about how we contribute to the planet and to the society, and how we can work in process that are more sustainable. It's what I see that in my case and with my colleagues, it's what drives us to keep going with our PhD projects. So that's ingredient, I think it's like so important for the young generation, like how with science we can live, we can give a better world. And I think that's a really important aspect of science and young generation.
Good. And I think this is a very nice final word if there are no more comments. But before we go back to our places and do whatever we do, I have to share a few things with you. And this is also for the young generations that you may carry to your supervisor so that you can so that you can share something in exchange. So these online talks are excellent, but nothing is, you can not do better exchange since going to a conference and meet there and chat over a coffee and whatsoever. So very close, and this is related to the December. We have in the Polymer Action Engineering community a conference in Scottsdale, the Polymer Action Engineering 11, and I hope you can see that. And who knows Tim? Tim is organizing it. Then you are sure that it is a very nice place. It is you will be assured of very good food. Registration is still open. You can still hand in abstracts. So whoever wants to go, it is a good place, and the climate is also good. So at least in Germany in December, the weather and the climate is not too good. It may be different in Lyon, but so if you would like to catch or have an opportunity to catch a little bit of sun and see a warm place, then maybe going to Scottsdale in December is a very good option. So that's the one thing I want to share with you.
Thank you.
And the other thing I want to share with you is that if you are still do not have enough about from discussing about polymer reaction engineering, we have a year 23. And if we go for 23, then we meet in Potsdam. So it is, we are going then to Potsdam with the Polymer Action Engineering community. It is the 4th international workshop on polymer action engineering. I have to admit, it is, the conference center is the left picture. We are not going to have the conference in the right picture, so not to promise wrong things, but Sanssouci is pretty close, so you can do that. Potsdam is a great place. You can come close. There is an airport close. There are a lot of cultural things around, and we can discuss about polymer action engineering. So save the date from September 5th to 8th in 2023. We will attach there the students' workshop of polymer action engineering, and so save the date, and if you like, we can meet there.
Thank you very much.
So that's
amazing.
So that's the very last thing that's left for me to do. I thank to all of our speakers that you participated, that you discussed. I thank to everybody in the audience for joining, for staying with us until the evening. Thank you, and maybe seeing you either in Scottsdale or in Potsdam or wherever. Thank you very much. Bye-bye.